Hey everybody, let's talk about the autoionization of water and the pH scale today. So if you have a beaker full of water, you have a lot of water molecules, and those water molecules are going to be constantly colliding with one another. And if you recall, water is curious in that it can act as both an acid and a base. It's amphiprotic. And so sometimes when the water molecules are interacting with one another, one water molecule is going to transfer a proton to another. And as a result, you'll generate a hydronium ion and a hydroxide ion. Now, this doesn't happen very much. Only about two water molecules out of a billion are actually going to carry out this reaction. But it does happen. And so what we're actually going to have is an equilibrium process where we have lots of water and we have some hydronium and hydroxide. Since this is an equilibrium process, we can write an equilibrium constant expression for it. Since water is a liquid, it doesn't appear in the equilibrium constant expression, and so all I'm going to have is the concentration of hydronium times hydroxide. This is such an important equilibrium process that we're going to give its equilibrium constant its own symbol. This is Kw, the equilibrium for water. And at 25 degrees Celsius, so at room temperature, this is equal to 1 times 10 to the negative 14th. Just like all equilibrium constants, as we change the temperature, the value for the equilibrium constant will change. But the bulk of what we'll talk about here in this class is going to be happening at room temperature because that's when we're going to be carrying out our processes. Since this reaction is a 1-to-1 ratio, for every hydronium ion that's formed, I get a hydroxide ion. In pure water, which we as neutral, we're going to have equal amounts of hydronium and hydroxide. And so if these are equal, I'll find that their concentration of both hydronium and hydroxide in pure water is 1 times 10 to the negative 7th molar. So in a neutral solution, I'm always going to have equal amounts of hydronium and hydroxide. And this is the fundamental definition of neutrality, equal amounts of hydronium and hydroxide. If I start adding stuff to the solution, I can change that. So if I add some hydrochloric acid, that's going to generate more hydronium ion. And so I'll increase that concentration of hydronium ion in that acidic solution. But this is an equilibrium. You always have to have the product of hydronium and hydroxide be 1 times 10 to the negative 14th. So if I increase the concentration of hydronium, then the concentration of hydroxide is going to have to decrease. And this is true in an acidic solution. On the contrary, if I were to add a base, something like sodium hydroxide, I would increase the concentration of hydroxide. Well, then in response to that, in order to reestablish equilibrium, since that product has to always be equal to that equilibrium constant, then the concentration of hydronium would decrease. And that would give me a basic solution. So in an acidic solution, the concentration of hydronium ion will be greater than the concentration of hydroxide, while in a basic solution, the concentration of hydronium will be less than the concentration of hydroxide. And this is fundamentally what makes a solution acidic, basic, or neutral, is the relative amounts of hydronium and hydroxide. So oftentimes when we talk about things being acidic or basic, we talk about it in terms of the pH scale. What the pH scale actually is a measure of the hydronium ion concentration in solution. So by definition, pH is the negative log of hydronium ion. And if I know the pH, I can calculate the hydronium ion concentration by taking 10 to the negative pH. This is a common log, so log base 10, and we're going to talk more about kind of how logarithms work and what they mean in class. In practice, what this means is that if we are at 25 degrees Celsius, again, if we're at room temperature, and we look at the concentration of hydronium in a neutral solution at 25 degrees Celsius, the concentration of hydronium is 1 times 10 to the negative 7th. Well, if I take the negative log of 1 times 10 to the negative 7th, I find that gives me a pH of 7. If my hydronium ion concentration is larger than that, so if I have more hydronium ion, then it turns out my pH becomes a smaller number. If I'm in a basic solution, my concentration of hydronium is going to decrease, and that will make my pH actually rise. And so a basic solution will have a pH that is higher than 7 at room temperature at 25 degrees Celsius. For the record, you can have pHs that are negative, and you can have pHs that are above 14. But most day-to-day things fall within that 0 to 14 range in terms of their pH. There is an analogous scale for the concentration of hydroxide called the POH scale. You've probably never seen it before, but we're going to use it this year. So POH is the negative log of the hydroxide ion concentration, while if I know the POH, I can calculate hydroxide by taking 10 to the negative POH. Again, if I look at my range of, how much hydroxide, how much hydronium do I have in a solution, when I have a neutral solution, both hydronium concentration and hydroxide concentration will be 1 times 10 to the negative 7th at room temperature. So that gives me both a pH and a POH of 7. If I have more hydronium than I have hydroxide, so if I have an acidic solution, then that means that my POH is going to be a larger number, while my pH is a smaller number. On the contrary, if I have a basic solution where the concentration of hydronium is less than hydroxide, since I'll have a low concentration of hydronium, I'll have a high pH, but my large concentration of hydroxide will give me a low POH. They are basically opposites of one another. And interestingly enough, because of the way log rules work, we can actually come up with a very, very useful relationship between POH and pH. And that is, again, at room temperature at 25 degrees Celsius, pH plus POH will always be equal to 14. So when we're working with an acid solution, it's going to be easier to work in pH. Oftentimes when we're working with a base, POH is going to be more convenient, but we can always relate the two because they'll always add up to be 14. When it comes time to measure your pH, there's a couple different options we have. So we can use both pH indicators and a pH meter. A pH meter is just a tool that basically is a wand, and you dip it into your solution and it'll give you a value for your pH. Whereas pH indicators will change colors depending upon the pH. They're actually chemicals themselves whose color depends on the pH of the solution. So you've probably used universal indicator. That's what's on that orange pH paper you use all through school, where red is acidic and a purple is basic or a blue is basic. Use phenolphthalein in first year chemistry, which is colorless in acidic solution and turns pink in a base. There's a whole bunch of them, dozens and dozens of them. They all have different color combinations or color changes that occur at differing pHs. So you pick the one that makes the most sense depending on what you're using it for.